All right. So, good evening, everyone. Astro 10. And today we are focusing on the sun. If you're getting this communication and you haven't done your exam number 2 yet, it's going to be closing at midnight. So, rush to the computer. I will be taping this, so you don't need to stay here. And then you can watch later. But I have only Allegra and Nika. So, yeah, one is a visitor, the other one is a physicist. So, no worries about it. Um, so what we're gonna be covering in the sun is basically its surface region. So what's going on in the solar surface, and then what's going on in the solar interior part, what type of cycles the sun goes through, and and also what sort of energy or powerhouse the sun is. So we have these different aspects to explore: atmosphere, the interior part, energy production, and cycles, solar cycles. So um, as we go through the material, or basically the slides that we have in our book, one thing that I would like to emphasize and call your attention as we go through all these different categories is the fact that the magnetic field, the sun's magnetic field, or the sun's magnetism, is is a key element in producing most of, if not all, the activity we observe in the sun. So when we talk about the solar cycle, we are talking about a cycle that is controlled by the sun's magnetism. When we talk about most of the solar surface we observed with telescopes like sunspots, spicules, Pleiades, flares, prominences, all these different episodes, coronal mass ejection, all these phenomena are pretty much guided or controlled by the sun's magnetic field. So when we try to answer the question as to why there is a reverse in temperature as you go from the solar interior, the temperature diminishes, go all the way to a minimum value in the solar atmosphere, and suddenly start to increase and rising tremendously, going all the way to the corona when it reached values of a million Kelvin, 2 million kelvins. So exactly what is producing this reverse in temperature? What is sort of a mechanism is responsible for, excuse me, transfer energy from the solar interior, not from the atmosphere, but from the solar interior, all the way to these outermost regions, and and warm up the gas in those regions. So again, magnetism and magnetic waves are or are the excuse me, the mechanism responsible for that. Um, so think about magnetism, and before I go there, I would like to, since I understand you are seeing my screen, I would like to go to NASA webpage and show some of the pictures available in there of one of the probes that happen to be watching the sun continuously. The Solar Dynamic Observatory is one of these missions. So let me, I mean, a figure is worth of several words. So let me use the pictures and the images and perhaps the simulations to explore the solar magnetism. So here we are looking at the sun's atmosphere. So, and the Solar Dynamic Observatory is a probe that observed the sun 24 hours for several days. In fact, it's up there for several years, and it's a continuation of the work and the project done by another solar observatory named SOHO, which I will also visit in a second. Except the Solar Dynamic Observatory has much better image resolution, and the images are quite fantastic. So take a look at this. Uh, Here is a sunspot. I just mentioned sunspot. Here's a sunspot coming into view. And as the sun rotates, you see the system kind of remains the same. You have a little bit of a deformation here and there, or rearrangement of these clusters. But it's just passed by. And down here, you have the size of our planet, just for comparison. Planet Earth is about 1/100th of the size of our star sun. And so what sunspots are? Again, sunspots are regions where the magnetic fields are very intense. The sun's atmosphere is pretty much heated. Its energy is transferred to the outermost region of the solar atmosphere by convection, by bubbling up of gas, hot gas, that transfer heat to that region. Now, in certain locations, the magnetic field, these field lines are so intense, this convective motion is prevented, is halt. And as a result, the region becomes cooler than the nearby photosphere. And the reason is you don't have the energy feeding that location. As a result, what we are seeing here is a contrast between these cooler regions in dark and the hotter regions in orange or yellow. Okay, so again, solar sunspots. When you go to the observatory, if you have the chance and you see sunspots, in fact, they are the result. They are the manifestation of strong sun's magnetic field in that region. Now, what we are seeing here is the so-called spikelets, and I will mention spikelets in respect to another region in the solar atmosphere called chromosphere. Spikelets are, let me take this sound out. So spikelets are jets of hot gas that rises up from the photosphere, from the internal region of the solar atmosphere, all the way to what we call corona. It goes into the corona, but they are not so big. They are about 7,000 kilometers in size. And these simulations show how magnetic fields, all these twisted lines, all this arch, represents the sun's magnetism. So the sun's magnetic fields kind of guide these jets and take them into the upper atmosphere as a result of the energy itself they have stored. So spikelets, they change over time, but they are very much visible against the solar chromosphere, especially during eclipses. And now, and because of the Solar Dynamic Observatory, we know spikelets are the result of magnetic field lines that have been measured. And I will go over details on spikelets in a second when I go over the slides. Another example, eruptions in the solar atmosphere. These are beautiful, beautiful, beautiful. So these eruptions, again, is the result of magnetic energy that is suddenly released in the sun. And so we are talking about millions Kelvin. So 1 Kelvin, 300 Kelvin is the equivalent of the temperature that we are used to, is a scale that physicists use to address energy in gas. So 1,000,000 Kelvin is a heck of a temperature. And this explanation, these slides attempted to explain how the sun's magnetism and its reconnection, how that energy is used to liberate such a profound and magnificent explosion called solar flares. And you're going to see again erupting here. Now we can see these bright areas are areas of high temperature in the solar photosphere that is also being indicated. So here is April 2nd and 3rd, 2017, several regions with flares over the solar atmosphere. You can see very nice, with very nice design, the magnetic field lines and the configuration of the sun's magnetosphere. You can see this blowing, this arching energy being pretty much released. Again, see how beautiful that is. So down in our slides, we'll see the sun's, the number of spots and the percentage of active regions in the sun. It has a progression that lasts for 11 years. So during 11 years, we see the number of active regions rising from a minimum to a maximum value. And the graphic here is going to be showing that. You see all this number of spots increasing as the time goes by. And at the end of a period of 11 years, this number, this percentage of spots, sunspots, have risen to a maximum value and diminished. And then it start all over again in another period of 11 years. And astronomers, by observing in detail the solar atmosphere, they found every single cycle of 11 years, the sun switch its magnetic polarity. So let's say in a cycle of 11 years, the sun dipolar field is north magnetic in the north geographic pole, the south magnetic pole together with the south geographic pole, and in the following 11 years, all of that is reversed. So the sun reverses its polarity every 11 years and making a total overall cycle or magnetic cycle of the sun in about 22 years. And this is what you're seeing here. So let's see, we have a cycle that is starting in 2009. So this cycle is going to be completed in 2009 plus 11 is 2020. So it's going to go down somewhat in 2020. And we are in 2017 there, right? Now it's going to start going down somehow and complete in 2020. So we are still in one of these periods. Now this Earth also, and we suspect all the stars, in fact, they go through these magnetic cycles. And this magnetism is pretty much generated in the sun by ionic movement of charges. So magnetic fields, as we study in physics, is a field generated once you set charges in motion. So the sun is a plasma that is constantly rotating and also subjected to convective bubbling up motions. And the combination of these two motions, the rotation plus the convection, generates a phenomena we call dynamo, responsible for these magnetic cycles. And here you're seeing how now the cycle is going down and is supposed to achieve a minimum value of active regions in 2020. So we are not there yet, and it stops right there, the cycle. Earth also goes through the cycle, but is not periodical, at least as consistent as the sun is. Earth, north magnetic pole, right now happen to be located in fact, the north magnetic pole of Earth now happen to be located in the south geographic pole. And the south magnetic pole happen to be located in the north geographic pole. That's why if you have a compasses, your north needle is going to be pointing towards the north, where the south magnetic pole is located. But Earth in the past had that polarity reversed, and more or less based on records on rocks, that the rocks tell us a story that this reversal goes in around 800,000 years to 1,000,000 years, but it's not consistent. It's not really consistent. And when the magnetic polarity of Earth reverse, so this might trigger some mass extinction, at least of some bacteria, because it is protected magnetosphere we have on Earth is going to be kind of twisted and get all crazy. So before I go to the slides, let me go to NASA SOHO, which is the other observatory. And they have very nice videos of the sun's atmosphere. Let me see if I about. So this is one video. So we have a coronagraph, which is a mask that blocks the sun and allow us to see what's going on outside the sun. So these jets, again, are pretty much controlled by magnetic field. But what's interesting here, you can see here and there some explosions occurring. See that? It's a cool one. Another one, major one here. And I don't know if you notice in the very beginning, there is something passing by. Let me show you. Right there. That's a planet. Or could it be a star? It's more like a planet. Yeah, those are stars. Let me get another video. That is in 2007. Yeah, 2017. There you go. The time is going by. That is in July. So as we saw in this SDO, the sun is not so much active these days. Up to 2020, we are experiencing a minimal. See if I can get better. These are not so good. No, that's 2017. I wanted something more older, where the sun was more active. Yeah, GIF movies, they are not putting a lot. Well, yeah, I should have put this on view. Okay, so let's go to the sun. So here is a picture, or is a cut of the sun's interior part. So you have pretty much the core, and the core has an important reason, and that is the core is basically where energy, the sun energy is produced. And what is the source of energy of the sun? It's pretty much fusion reactions. Fusion. It's not fission like nuclear power plant. What they do, they take uranium or these radioactive heavy atoms and they break them down. And as you break these unstable atoms, you release energy. And then you have to cool down the environment where this breaking down process is operated. Now, fusion is a different process. It's one where you take lighter atoms like hydrogen or helium or carbon, and then you fuse them, which means you fuse the nucleus, and then you create a heavier atoms. So in fission, you break down heavy atoms into smaller one, and you liberate energy. In fusion, you fuse the nuclei of lighter atoms, and as a result, the resultant atom, which is heavier one, if you calculate the total mass of the resultant atom and the total mass of the atoms that fuse to yield that new heavier atom, what you found is the resultant mass is slightly less than the combined mass of the parent atoms, which means where did the mass go? It goes into energy. So basically, this excess of mass that goes, or this missing mass, is converted into energy as a result of that important equation that Dr. Einstein gave us, that some people call that mass, as we know, is crystallized energy or crystallized electromagnetic radiation. So this missing mass, in fact, is converted into gamma rays, gamma rays, gamma rays. So gamma rays are pretty much light of very high frequency. It's a very high frequency. You don't find abundantly gamma rays on Earth. You find gamma rays associated with exploding stars, supernovae, the nucleus or the interior part of the stars, but not here on Earth. Earth is a cold place. So the core of the sun, or the core of a star, that is called the main sequence, is where, is where energy happens to be produced, right here. It's about 25% in radius of that region. Now, these fusion reactions generate energy. In fact, you take 4 atoms of hydrogen, and as a result, you produce 1 atom of helium, which is slightly heavier, plus neutrinos, and neutrinos are very light particles that interact very little with matter, plus gamma rays, plus electromagnetic radiation and gamma rays. And gamma rays, this energy, is what keeps the sun stable. So we saw when we studied star formation in chapter 5, we saw that as stars happen to be formed, they contract as a result of gravity. So gravity eventually, or depending on the conditions of the giant molecular clouds that initiate the star formation, so depending on whether or not in different locales of these hypothetical giant molecular clouds, if the density is good enough, gravity will take over, will kick in, and initiate a slow process of contraction. Now, the contraction follows with a gas that heats up, that becomes hotter. And eventually, the center part of this system becomes so hot that fusion reactions take place. And then we say the star becomes stable, becomes a main sequence star, is when these fusion reactions take place, and energy, gamma rays, energy start coming out of the center part. Now, this gamma rays flies and migrates outward. We call that this migration process, we call diffusion. So this diffusive energy migrate and pass through the interior gas, transfer some energy to it, keeping the sun from collapsing under its own weight. So now we have a situation we call hydrostatic equilibrium, and this is very important. Hydrostatic equilibrium. This is here's the formula that I was mentioning before. So hydrostatic equilibrium, where is the hydrostatic? I don't see anything. Hydrostatic equilibrium. I thought they had a hydrostatic equilibrium. So this is an example. Yeah, the narrative here is about hydrostatic equilibrium. At each point within the sun, the outward push of pressure is balanced out by the inward pull of gravity. So we have these two conditions occurring at any given radius from the center part. So the gas pressure, which is pretty much built up by energy produced in the core and that is transferred to the gas itself, this gas pressure halts the collapse, the contraction of the sun into what could be a black hole, right? So you have this energy, this source of energy that keeps the sun stable. And we call the stability between the two forces, the balance between the two forces. One is pretty much the result of gas pressure. The other one is the inward pull of gravity. When these two forces balance out, we call the situation hydrostatic equilibrium. Oh, it's right here. There you go, hydrostatic equilibrium. This is important. It's a technical term, but it's important. So stars, they are mature, they are in hydrostatic equilibrium. Pre-main sequence stars, stars that are evolving to become giant stars, supergiants, and Cepheids and R. Lyrae. They are not in hydrostatic equilibrium. They are either expanding or contracting, or they are doing both. So R. Lyrae, they expand and they contract. They expand and contract in time scales of a few days. No, in fact, less than 1 day, as opposed to Cepheids, which are bigger stars, but they also pulsate. They are not in hydrostatic equilibrium. So they expand because they want to release energy, build up in their interior part because they are evolving, and in future chapters we are going to explore that. But as they expand, energy is released, but then they collapse again under their own weight, and they keep kind of like an harmonic instrument going, expanding, contracting in time scales of a few days sometimes, and that this process is pretty much associated with the amount of energy they release eventually. So again, so we went over the core. That's where energy is produced. Now there is a second region in the interior part of the sun that's called the radiative diffusive shell. See this shell here in yellow? This is pretty much a region where energy produced in the core moves outward towards a third interior region, which is called the convective zone. So here is the convective zone where mass transfer occurs. So basically, hot gas in the lower region rises up, bubbles up, and transfer heat to the upper regions. And then it cools down and then falls back to the hotter regions. And then you have this circulation going on and on and on. It's called convective zone. So the last stage of the convective zone, so you have three regions in the solar interior. The core itself, where energy is produced, the radiative diffusive shell, where this radiation migrates and moves outward, and the third region is the convective zone, where the mechanism by which energy is transferred is slightly different. It's by bubbling up, like a pretty much like a we have convection here on Earth. Our Earth mantle, which is the region between Earth core and the lithosphere, which is the external brittle region, the mantle is pretty much solid core, solid rock. But it's solid rock under so much pressure and so much of a high temperature that it moves. Like if you put ice, which seems to be solid, right? So if you put ice under high pressure, ice moves and behave like a fluid. And that's why glaciers moves and carved beautiful valleys like the U-shaped valley in Yosemite Park. That's why glaciers carry sediments, moraines, and create mountains of sediments. So, so this pretty much convection is a movement that exists in our mantle as well as in the solar convective region. So those are the three main regions of solar interior. You should pay attention to it: core, radiative, diffusive shell, And the third one is the convective. I had to buy a different stylus. My stylus is bad. Convect, radiative convective zone. Zone. There you go. So energy production. Energy is produced when, basically, if you go to the so-called PP chain, is a proton-proton chain. In the solar core, the temperature is so high, the hydrogen atoms are not like a hydrogen atom, which consists of a proton and an electron attached to it. The electrons are free because it's too hot. So we have protons kind of free. So what happens, two protons merge together and forms a isotope, an isotope consisting of a proton plus a neutron. So it's an isotope called the deuterium. And then two deuteriums merge together, forming an isotope of helium, and then eventually the helium normal atom is formed, and then we have the fusion completed. You don't need to memorize this PP chain, but you need to know the details of it. At least once in your life you saw that happening. Let me see what else. Here's that's a nice picture that shows these three interior regions: core, radiative shell, convective zone. Okay, so much for the solar interior. Let's take a look at the solar outer region. So the solar outer region is also divided in three main regions, and we call these outer regions an atmosphere. Atmosphere. So the solar atmosphere is divided in three regions. The one that is most interior, the one that is closer to the core, is the so-called photosphere. So photosphere is a sphere of photons. Photons are particles of light. When you look at a star, you see stars at nighttime, what you're really seeing is the photosphere, because that is the region from which light escapes. And then once light escapes, you collect with a telescope or with your eyes, and then you identify the star. So photosphere is a region by which the energy that was produced in the core, in fact, millions of years ago, the sun, according to calculation, that energy produced in the core, called gamma rays, diffuses itself through the radiative diffusive shell and takes 1 million years to migrate and diffuse itself in energy to the atmosphere. So what was a gamma ray in the core become optical light in the surface, and then escapes. The gas does not trap anymore, right? So the photosphere is that region, the sphere of photon, and there are typical effects on it. One is the temperature drops. It goes from 20,000 Kelvin all the way to about 4,000 Kelvin in the lower possible temperature. Above the photosphere is a region called chromosphere. So chromosphere is the region, as we saw in the beginning of when I show you the Solar Dynamic Observatory, is where the spicules go through, is where these magnetic fields manifest itself, guiding these jets, this hot gas called spicules. So chromosphere has this name, is a sphere of a chromium, because when the sun goes in eclipse, so the moon blocks the sun, we call that solar eclipse, we still can see the spicules going above the shadow the moon itself produces, and it has a kind of an orange or chromium coloration, and that's why the name chromosphere. But as we study light, astronomers identify these chromium coloration as hydrogen H alpha line, the transition, and it's pretty much hydrogen. So chromosphere, we still have the name, but there is no chromium there producing there. It's pretty much hydrogen H alpha line that is produced and escape out of these spicules. And the third region, which is the most extended and is also the less dense, is also the hotter one, is called corona, solar corona. So let's take a look at these three regions. So here in this picture, the photosphere appears as a bunch of little cells. So these cells are the result of the convection zone. So the photosphere, this lower region of we call photosphere, is sitting on top of convective zone that has all these bubblings. Now, if any of you or some of you decided to study astronomy and take upper division courses, one of the things you learn is that all these convective cells are big, gigantic bubbles. As they bring material up to upper regions, when they hit regions of lower density, they tend to break themselves. So they are not kept big enough. So as you move away from the solar interior, they become smaller. So they break in size, and the last generation of this bubbling process is what we see in the photosphere, and we call this phenomena granulation. 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 So granulations, each one of these cells here has the size of 3,000, 4,000 kilometers, 3,000 to let's say 5,000 kilometers. 5,000 kilometers is about 3,000 miles. Just give you one idea. So 5 kilometers, 5,000 kilometers, 3,000 miles. That gives you an idea of how large these cells are, and they short-lived. They live few days, and if you have a video of these bubbles, in fact, they look like soup. When you make a soup and start bubbling, it's kind of the same idea, sort of. That's the photosphere, average temperature 5,800 Kelvin. Chromosphere is the regions where the spicules are. You can see spicules very well defined. See this kind of a, you can see probably better here. See that? A bunch of little spicules, but let me see if I can get a spicules better in my computer. Just a second. How do I get rid of you guys? Wait a second. There you go. So I can pretty much go here and spicules. I can give a better view of spicules images. No, sun spicules. There you go. Here, right here. See, this one is very good. See these spicules? So those jets. So what you see in the bottom part is photosphere, and you can see the granulation in there. So this granulation, these grains, are pretty much bubbling up thing. Now the jets, the spicules, they go into the chromosphere, and now we know is a byproduct of the solar magnetism. So magnetic field lines are pretty much thinning and controlling these jets. You have another view of it. These prominences and the flaring occurring. You can see the spicules in there. You can see the granulation quite well in there. Okay. Corona. Let me let's see, one question. Rank these layers of the sun in the correct order from the coolest to the hotter. So the coolest one, this question is complicated because see, the photosphere has an average temperature. A photosphere goes from 50,000 to 4,000, 3,000, 4,000. The region from where the radiation, most of it escape, is 6,000 Kelvin. 6,000 Kelvin. Chromosphere, it depends. It goes from 4,000 all the way to 10,000 Kelvin. So, but depending on which line you look, you could be talking about 8,000 Kelvin. So I would say that photosphere, chromosphere, and corona would be the one. The hottest certainly is corona. Photosphere, core, and corona. What a core? No, this is wrong. I don't know where this is, but it's photosphere, chromosphere, and corona. Now, solar wind. Solar wind is again like evaporation. So you wash your hands are what? So hot outside, and then the water evaporates. So basically, water molecules are able to break through their surface tension because with the heat, they vibrate faster to the point they are able to break through the surface tension, and then we call that process evaporation. So the solar atmosphere, the gas, the molecules also, the protons and electrons are in constant motion. And sometimes their motion is such, they achieve speeds that are high enough to break through the gravitational pull of the sun. And sometimes if we are talking about charged particles and they tend to be attached to the magnetic field, then they might be able to break through the magnetic field, and you have sun evaporation. So the sun is constantly losing particles as well as all stars. But there are global mass loss that certain stars go through, and the sun is not an exception. So this mass loss of the sun is called solar wind. So solar wind is a wind that is different from here on Earth. I mean, here on Earth, when you have a wind, what you do have is you have a differential pressure, gas pressure, and then air mass or atmosphere moves from the region of high pressure to regions of low pressure, and then you have what we call wind. Now, in the case of the sun, the solar wind is ejection of particles pretty much guided through magnetic field. So in the region where the solar wind is occurring, the magnetic field lines are open, are pretty much anchored on the solar atmosphere, but open to the solar system. And then you have this ejection of particles in a direction that is pretty much guided by the sun's magnetic field. And these particles eventually they might lose their grip from the magnetic field if they are too far away, and the field itself becomes weaker, and then they just move independently from the field. But the ejection itself, the process of accelerating these particles, is pretty much transferred to them by the sun's magnetism. It's a wave phenomena, is a wave type of effect that has a combination of sound, acoustic waves, and magnetic waves. But those details, you don't need to worry about it. Just to say, the solar wind is somehow guided and controlled by the sun's magnetism. And you can see more or less here, right? So all these twisted lines are pretty much sun's magnetism. Sunspot, we already show, is a result of cooler regions. Here's the 11-year cycle. 1975, you have a minimal in the number of sunspots observed, it gets a maximum and then falls down about 11 years later and repeats again and repeats again. So, but again, as I mentioned in the beginning of this talk, the polarity of the sun, if you think about the sun as a dipolar, global dipolar field type of object in space, the sun's polarity reverse every 11 years. It doesn't mean the sun itself goes somersault, right? It's just the magnetic polarity. So what is north magnetic pole in 11 years reverse, and then you have a reconnection going on, and then you initiate a new cycle. The sun's integrity is there always. It doesn't change. The sun has a rotation, all right, so but the sun doesn't go somersault. The polarity is reversed as a result of this dynamo effect I was mentioning. Another thing the astronomers observed was in the beginning of a cycle, when the number of spots start to rise, the spots appear at a high latitude, and that's what you see in the diagram below. So we have a bunch of spots appearing in the beginning of a active cycle, and as you count more and more spots, they tend to appear more closer to the solar equator, both in north and south latitude. And this diagram has a name. The name is butterfly diagram because it looks like a butterfly, right? And it's very consistent and very repeatable. And here they are. And some things that when the sun becomes very active and it shoots out lots of particles, the solar wind is intense, then perhaps these particles, protons and electrons, might interact with the upper atmosphere, Earth atmosphere, and might trigger weather changes. So there is a lot of work done in trying to connect solar activity with weather patterns here on Earth. And there is a period where the sun was not observed any spots. It's called Maunder minimal. And then some people try to relate that with the period of drought in Europe. I don't know if this is confirmed or not, but I'm just saying. Everybody says, so I will say too. And pretty much that's it. That's the magnetic flip, which I was mentioning about. And the more active regions, prominences, are these big arcs, again controlled and guided by by sun's magnetic field. In this picture, you have a little Earth there just for comparison. See that? Of course, Earth is not there, but it's just for comparison, so we can see it better. There you go. It's a little Earth there. And pretty much that's it. So that's the sun. So think about the sun, the interior part, 3 regions, the exterior part, the atmosphere, 3 regions. The solar source of energy is fusion reactions, hydrogen, 4 atoms of hydrogen, 1 atom of helium, excess of energy through gamma rays, and neutrino is a very is a particle that does not interact much with material, pretty much escape once it's produced. And some of the main names of solar active regions. Okay. I know Nikia is not in astronomy. Michelle Zunig, I think you are not in astronomy either. Allegra, do you have any question regarding astronomy, this sun thing? Oh, let's see. Did I take the sound? No, I have a sound there.
Nope. I said thank you.
Oh, okay. All right. Now I can hear you. All right.
Thank you.
Okay, good enough. I'm gonna open the bar now for physicists. So Allegra, if you want to hang out, that's fine too. But yeah, okay. All right, physicists, go on, shoot it. What's going on? Oh, wait a second. Let's stop tape.